So here are the 6 basic parent functions, and we're going to be working with these all week. We're going to be doing transformations of them. Now, we're not actually transforming anything today. Instead, what we're going to be doing is looking at graphs that have already been transformed, meaning they've been shifted or rotated or whatever, and we're going to pick off pieces of valuable information from them, okay, key features. And so these are our 6 basic functions. What was the very first one from your packet? Linear. And what was the name of it, though, on your packet? It wasn't linear. What did your packet call it? Starts with an I. Identity. It's okay if you give me as an answer linear, because we're so used to saying that. But your textbook calls it identity as its parent name. And so I'm going to call it identity just to be consistent. After linear, that's degree 1. What does your packet call degree 2? Square. And what does that look like? Remember the name of the shape? Makes like a U. What's the mathy word for that? Starts with a P? Parabola. And then, what's the inverse of square? Square root. So now the inverse of something literally is you just switch the x's and the y values. And what that does in practical terms is it flips the graph over the y equals x axis. And what that means this graph would do then is basically rotate to the right. However, it doesn't have the lower part of the graph because in the xy coordinate plane, those values below the x-axis down here, y would be negative, but in the real numbers, there's no y value where you would take the square root and it would give you a negative value. And so that's why there's nothing here under the x-axis. It's strictly above because all those values are positive. And those are inverses of each other. So that's the square root parent function. Increasing the degree one more time gives you what kind of graph? Cubic, right? And that one looks like this. Bless you. So this is cubic. Okay, x cubed. And what's the inverse of cubing something? Cube rooting it, okay? And when you take the inverse of a graph, it gets reflected over y equals x. That means this graph rotates sort of like 90 degrees-ish, kind of. Looks like this. And that's cube root. And the reason why it has y values that are negative is because you can take the cube root of a negative, right? The square root had no y values that were negative because you can't square root a negative, but cube root can. And we had one remaining graph. Which one am I missing? Absolutely. I know. And the absolute function looks like a V. Absolute value. And this graph makes sense. This is kind of goes along the same lines as the linear graph. But if you think about it, it takes all of the negative x values here that would have been sloped down, makes them positive, and so that rotates it over the y-axis. And now they're all going that way. So it kind of looks like a linear or identity y equals x, but takes all the negatives and makes them positive. And that's why it looks like a V. Okay, and so these are our 6 basic functions that we're going to be talking about for the rest of the week. Tomorrow we're going to do single transformations on them. We're just going to move them one way. And by the way, I won't be here tomorrow, so I'll have a Google Classroom video for you to watch for your notes and then your homework, so you should be fine. The next day we'll do more than one transformation. And then on Thursday, what we'll do is we'll be given a graph, and we'll use information from it to write the equation ourselves. So the next few days we'll have the equation and we'll do the graph. Thursday we'll be given the graph, we'll write the equation. And Thursday will be our last new material before your test, which is coming up when? Monday. So we'll be working on the review Friday. Before we move from this screen, there's a few more vocabulary words that we need for this lesson. And so we're going to be labeling some stuff on here. If you look at the square function and the absolute value function, they have this point right here where they change direction. Remember our vocabulary, a mathy word for that point? Vertex. That's right. Those are called vertices, right? Vertex. So that's a vertex, and that's a vertex. Yep. Another thing special about that vertex is that it's right dab smack in the middle of the graph, okay? And there's an imaginary line that runs through there where what's on the right side of that line is just a reflection of what's on the left side. Do you remember what we call this line? Axis of symmetry, right? Instead of it, not the axis of evil. The axis of symmetry here. And this also is an axis of symmetry right here. It's an imaginary line that splits it in half, okay? And so it's a reflection on either side. And we're going to talk about how to write an equation for that line here in just a minute. So only those two graphs have a vertex, but some of the other graphs have special points, they just have different names. So for example, on the cubic and the cube root graphs, this special point where their behavior changes a little bit, these points are called inflection points. And we'll be looking for those points when we start doing transformations. We'll be using that as a point to help us figure out where our new graph should go over the next couple of days. The identity function doesn't really have any special points because there's nowhere that it changes behavior. It's just doing the same thing everywhere. So that one doesn't have any special point, but on the square root function, this point right here, we're going to call that the initial point. And that makes sense because initial means like where something begins. Like when you say initially, you're saying, before, in the beginning. So we're going to call that the initial point. And it's good to have vocabulary words for those things because when we start doing transformations, I can say, okay, where did the initial point transform to? Or where did your vertex go? Or what happened to the inflection point? And you want to be comfortable with those words. Does anybody need this up anymore? Okay. So what we're going to do for your notes today is I'm going to work through one problem with you and then give you some time to work through the rest, and then we'll go over them together. Real quickly though, did y'all picked up those blue sheets right there? Give you time to finish your notes on your own and we'll talk about it. Take a minute and just read all those words up there so you can get an idea of what it's asking us to find. assume on all your graphs that when it goes off the graph, it's going on for infinity. Okay, let's begin. So this is a transformed graph. You can tell it's going down, which means the a value is negative. The vertex has shifted because it's not at 0, 0. What is so part A asks us to find or identify the function family. What is the name for this function, the general name that we wrote? Juan, what do you think? Well, so look at the shape of it. And from these notes over here, which one does it look like? Square. So that's what it's asking. So all the names we wrote here, that's what part A is asking us to write. Is it identity? Is it square? Is it square root? Etc. So going back. So the answer for A is square. I would take quadratic if you put quadratic. Right. B is bossy. B is for bossy because B is asking us for 1,000 things. And so what is the very first thing it's asking us to find? End behavior. So here's what end behavior means like in mathy words. End behavior means this. What are the y values doing as x goes out to negative infinity? So as x goes left, what is y doing? Which way is it going? Down. So that's your left end behavior. And I'll just you just welcome to write arrows for that, okay? Whichever arrow you put on the left is your left end behavior. And the end behavior on the right means as x is going out to positive infinity, what are the y values doing? Where are they going? Down as well. So it's down. Down, down. Remind me to play for you the Led Zeppelin song that I think about every single time I say down, down. Every single time. Every last blessed single time. Is that all that B is asking me for? No. Matthew, what is it asking me for next? Vertex. All right. So by the way, this point right here is the vertex. I'm sure you're all good with that. It looks like it's a half value, like it should be half or something, but the directions say that everything has integer values, which means a whole number. What's going on here if that's supposed to be a whole number? What is it counting by? 2. Your scale is 2, right? 2, 4, 6, 8. So if the scale is 2, what is the x value for that point? And what is the y value? 9, right? Because it's going 4, 6, 8, 10 right there. So the vertex is 1, 9. Please write it as an ordered pair, as a point, with parentheses, with a comma. So let's talk about the axis of symmetry. So I heard someone say 2. That's close. No, 2 is the correct, sorry, no, it's not close, sorry. 1. But the axis of symmetry is an imaginary line. So you want to write it as an equation of a line. What is equal to 1 everywhere on the axis of symmetry? Is that an x value or a y value? Y is changing here. So look, this is my axis of symmetry. X is unchanging everywhere. No matter which point you pick, here, x is 1. Here, x is 1. Here, 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 here. Everywhere on that line, x equals 1, right? The y value is changing, but x is constant. So this is an equation of a vertical line. X equals 1, because it's 1 everywhere on that line. If I wanted to write the equation of a horizontal line, what would it start with? If it was going like this, horizontal, it'd be a y equals something, right? Because y would be the same everywhere on a horizontal line. What is it asking me for next? X and y intercepts, okay? X-intercept, remember, is where the graph crosses the x-axis. How many places does this graph cross the x-axis? Dos. Once here, And one's there, that's right. Hayden, what are the points for these x-intercepts, please? Negative 2, 0, and 4, 0. It also asked me for the y-intercept, but here's the thing. Let's say you got bored of this problem in part A, right? And you just kind of go through, you wake up a little bit here for the y-intercept, and you look at the graph and you go, aha. Bless you. 1, 9. So that's the y-intercept, it's got to be, right? That's the vertex. But slow down. Like I get people, they get taught, it's very repetitive problems, and when that happens, your brain zones out, and you're not paying attention anymore. But that is not your y-intercept. The y-intercept is where does the graph cross the x-axis, and that's right here. And what is that point? 0, 8. Okay. Y-intercept is 0, 8. Is that all that Bossy B asked us to find? Right? I think I did all the things. Okay. C is asking for domain and range. Take a minute and write down what you think the domain and range is if you haven't already done so. Kat, prepare your answer for domain and range. I'm going to ask you in just a second. Prepare thyself. Yes. Kat, what do you think for the domain? Negative infinity to infinity. Perfect. So that's the domain. And the range means the lowest value to the highest value. What's the lowest value, of the lowest boundary of the graph? Cat. I'm asking Cat. Negative infinity gets a parenthesis. And what's the highest y value? 9. And do you think that would get a parenthesis or a bracket? Perfect. What would have to change on the graph for 9 to get a parenthesis instead of a bracket? An open circle, right? What I want you to do is take a few minutes and finish your notes. This is not phone time, okay, because it's not your homework. This is still the lesson, but I want you to spend some time working through the problems. They don't all ask for exactly the same thing as this one because they don't all have an axis of symmetry or vertex, for example. They have their own special things because they're each unique in their own way. So you need to read the directions, and then we'll go over the answers together, okay? All right, here is the next one with the square roots. You'll notice that there is no left end behavior. So for my notes, I put DNE for does not exist, or you could put the word none, or you could put, excuse me, NA for not applicable, whichever you like. The other things that I want to mention to you, for the range, people, okay, because look, if you do your domain left to right. So then when people go to find their range values, they want to list it left to right as well. They feel like it should be 2 to negative infinity. They want to go from like this way. But remember that you're always writing your intervals smallest to biggest, right? Least to greatest. You'll be amazed at how many people will give me range and they'll put 2 to negative infinity because really they just haven't rotated their brains around the coordinate grid correctly. It's lowest to highest when you're doing your y values, and that's why it's negative infinity first and then 2 second. So be careful about your order. Be sure that you have straight brackets because there's no open circles anywhere. Okay. Questions about anything here? Y'all are good? Okay. And just, as a preview of transformations, 3 things have happened here. It went to the left 4, it went up, or actually 4 things. It went up 2, it was stretched by 2, and it was reflected over the y-axis, right? That's all the different transformations, which we'll be talking about and reviewing the next few days. Absolute value transformation. There are two x-intercepts, one y-intercept. There's your domain and range, and value, and behaviors up, up. It was stretched by 3. That's why it looks real steep and not spread, not fanned out more. Good on that one? Next, a cube root. Does anybody need that one up anymore? Cubic. Is this the last one? Okay. And then I have some papers to pass back to. One of them is your quiz. I'm going to go over the quiz under the Elmo, so if you have a question, just wait till I've passed everything out, and then I will go over it. If you've been waiting on the bathroom, you may go now.